My name is Kinsey Skillen. I'm an assistant professor at Texas A&M. I have a project I want to discuss that's in the infancy. And so I'm only going to be able to touch on sort of our test setup, our background, our ideas of how we want to test headed and hooked bars in these beam column structures. But I'm only going to be able to touch on the headed bar component just for the sake of time. And this talk is a portion of a very large study that's funded by our Texas Department of Transportation. So I want to thank certainly faculty at Texas A&M, Adolfo Matamoros at UTSA, who's going to do some subcomponent testing. Obviously, our graduate student here in the room, Josh Henson. And so again, keep in mind, there's a lot of tests that we're going to do, but we're going to stick with just the headed bar component. For those of you who don't know what a headed bar is, just think of it as a nut that you put on the end of the bar to anchor it a little bit better than just pushing it long lengths, where sometimes you don't have the distance to do so. So the research question that we've determined is, can you get similar joint strength, and then I added this deformability component, to improve the joint with headed bars compared to their existing detailing practice. And also, because the structures that we see in the field, they're large, and we want to make sure we can improve the constructability as well. And so when we were tasked to determine what structures might be most useful or might benefit from using headed bars, we started to go down the list of all the different configurations of structures that TxDOT uses. And this is one of their straddle bent structures. I'm not sure why they call it a bent, but basically it just spreads the columns around the roadway so you can keep traffic without impeding traffic, and you can run your what they call cloverleaf roundabouts without obstructions. And so those joints up there are a prime candidate for headed bars. And we'll talk about this in a little bit more detail. They also use these multi-pier bend caps. This is pretty common for bridge structures, but obviously in this region here where you have bars being terminated might be a good place to put headed bars. And finally, one of the other bridge structures that they use, and they kind of scare me, are these cantilever bends. They grab the roadway above by kicking off a beam from the column. And you can see some different configurations there. And the issue is they can't always run a continuous bar around the joint because of the way they're constructed. They form up they form up the column. Reinforcement bars need to then be spliced, and they're splicing it in the joint, and it can be kind of worrisome. If we go back to the simple straddle bent structure, and we dig into the details, their standardized details that they use for such structures, you start to see how they splice the joint. It's a bit difficult to see, but basically they splice the column bars to a hook, and then they splice the beam bars to that hook. And if you zoom in, you see it here, but by overlay on red, just one layer of spliced reinforcement, you see it there. So they're splicing the top beam into the joint, and then they splice the column. And again, these are continuous joints, and so they're getting the grunt of the moment in the joint. It worries me a little bit because we all know how vulnerable splices are to failing, and when they fail, this whole thing could let loose. They do the same thing in their cantilever bents. This is a sort of double cantilever, but it's offset, so you do get some negative moment in the joint, and the way they get them bars into the beam is by splicing them or coupling them sometimes with bars that are protruding from the column as they sit. And so, as you can imagine, you have to install a coupler in the field, make sure it's straight, and, well, make sure that those bars that are spliced in the column also stay put. And so we thought, well, you could potentially go to ACI, and there's been a lot of headed bar tests that have been done, but you start to see the difference between some of the sizes of tests that have been conducted on hooked and headed bars in the current 408 database for heads, and then you look at some of the sizes of specimens that we're dealing with here in bridge structures. And again, these could still be applied to larger scale beam building elements, but you start to see maybe, well, if I have one layer of reinforcement and I use heads or hooks, you get some sort of strength with that group. But you start putting many of them, lumping them in the same spot, how confident are you that that's going to stay put when it's subject to vertical loads from traffic and long bridge spans, which are not light? In addition, they use straight lengths of hook or bars to terminate in those multi-pier bent caps. So we think that a good use for headed bars would be in these regions as well, where they don't seem to run them up very high, but because there might be less moment in those regions, maybe it's okay. But we're still going to look at the effects of having them in these configurations as well, because they're in a circular configuration, which we haven't seen test data on. So if we go back to the straddle bent, the one I've been talking about, and you look at the demands, there's vertical loads, lateral loads from traffic potentially going around the curve, and the sizes of these things are 60 feet plus, 60-foot spans. They're no joke, and the cross sections are 8, 10 feet in diameter, in width. So if we wanted to test one of these in our laboratory, we have to start thinking of what are the in situ demands on the structure. And so from the gravity loads, you can see that you get some negative moment in the joint. Because the bases are, restrained, you develop some axial load in the cap beam as well. And when you look at the lateral load, you get some joint closing on one side, joint opening on the other, right? So the moments are opposite directions depending on which side of the joint you're on. And so if you superimpose those with the gravity load, you get some resultant that's some joint closing and some joint opening with some axial force. That's the takeaway there. And so what we've decided to do is to snip out some piece of the structure in that region up there, right? And we've come up with a test here that's might be a little complicated to think of, but if I move over here and I snip out that joint, this is this box here is the same as this box up here. So all I need to really do, if I want to get that moment diagram, is we need to be able to push down or pull up to get joint opening and closing. But if you remember, it's got axial force on it, so it's keeping that cap beam in compression. And even when it gets a little side sway, it still stays in compression due to the magnitude of the vertical load. And so we want to push on the cap beam and keep it flush. If you notice, in the column, there's still moment down here. And so what we're going to do is we're going to restrain it, this location here, clamp the heck out of it to our wall so that this joint here stays more or less fixed. And it can transfer the moment here. Minimal shear in the column. And again, we're going to push the beam out to nearly the inflection point, so all I have to do out here is just push and pull down. I don't need to apply any end restraint to transfer moment out there. And this specimen, by the way, is full scale, and I'll show the dimensions here in a second. We're also going to cast it in place just like they do. TxDOT doesn't like to do things on the side, casting position. It's not the same way that they construct it in the field. So we're going to cast this thing vertically, just like they do in the field. So we have these big FCO forms that are 5 by 6 feet, and cast it in place just like they do. Fly the column cage in, and then cast the beam up in the air. These beams are going to weigh 80 to 100 kips, wet concrete in our laboratory, but that's how they want us to have it done, and so that's how we're going to do it. And there's just kind of a Mickey Mouse rendering of what it could look like. 13 feet tall. This will be about 24 feet. And we have one or two of our 590 kip actuators. If someone was standing on this, their head would go to maybe the top of one of these rungs here. So it's going to be quite large. The cap beam is 5 by 4.5. The column is 4 by 6. And so as I mentioned, with this loading configuration, if we're looking at just this window of the cross section, and I push or pull down, I can get these moments that I want in the joint, either opening or closing, while still maintaining the axial force in the beam, because it might have some effect on the joint. So that allows us to then test all of these things that we don't quite well understand. One of them being, and I apologize for this being kind of busy, but the takeaway here is when you have multiple bars, groups, arrangements of heads being developed in the joint, you don't know how it's necessarily going to work. And so we need to be able to apply some sort of load to that system to investigate the effects of having many layers of bars, bars that have different stresses on them, right? And then also the geometry of the bar itself. And maybe I should have started with this, but this is just a very idealized rendering of how we could improve a joint with hooks or heads by sort of cross-hatching them in the joint. Again, this is just very preliminary. But when you do that, you develop some struts in the joint and cause cracking. So there's some different ways we need to think about how we orient those bars. I'm running out of time. And so you could potentially cross more of them, remove the layers around, disperse some of the joint shear, engage more of the joint. So there's some ways that we think we can take advantage of hooks or headed bar configurations to improve upon the splices that are currently being used. I want to get rid of those splices if we can. And so where we stand, well, there's a lot of moving parts to this. As I mentioned, this is only a year into this project, and so we have some tests that are going to be performed at UTSA, some smaller subscale assemblies. We have a large-scale test, 3 of them being performed at our high bay lab in College Station. And so this is just a quick snippet of one of the cages that the student was working on last week. So you can see, no joke. TxDOT wants to see it full size, just how they build it in the field, and under similar construction sequence. I'm right at 12 there, so I'll end it for questions. We got 3 minutes?